Okay, in this tutorial we're going to be looking at roots of complex numbers. Okay, so square roots of complex numbers. If z squared equals x plus y, if z squared equals x plus yi, okay, then and r equals cis theta, then z can be found using two different ways. Okay, so we can do it by the rectangular form, or we can do it in polar form. Okay, so we'll look at the rectangular form first. Okay, so we've got z squared plus 2 plus, z squared equals 2 plus 2 root 3i. We want to find the complex number z using the rectangular method. Okay, so what we do here, okay, is we replace I squared with -1. Okay, so we say, okay, if we've got z, we let z equal a plus bi, okay, then z squared, okay, equals a squared take b squared, okay, plus 2abi, okay, is what we look at doing. Okay, and then what we do is we equate the real and imaginary parts. So we say really that, well, z squared is all this, okay, but z squared is also all this. So this is our real part, okay, and this is our imaginary part. Okay, well, we know this is our real part and this is our imaginary part. So we know that now that a squared take b squared equals 2, okay, and that 2ab equals root 2, is 2 root 3, okay, as well. Okay, and now we can solve this via substitution. So what we need to do is we need to rearrange one of these. Okay, so what we'll do is we'll rearrange this one for b. Okay, you won't want to rearrange this one, that one's a bit yuck, so we'll rearrange this one. Okay, so we'll say that b equals, when we divide by 2a, our 2's will cancel out, so we can say that b equals root 3 on a. So we can substitute into here now. We might come up here and say that we've got our a squared minus root 3 on a squared equals 2. Okay, so we get a minus 3 on a squared equals 2, just by expanding this bracket. Okay, so then you multiply by a squared, so we get a cubed take 3 equals 2a squared. Okay, so you get, so this is a squared, so this will be a to the 4. Okay, so then we say we got a to the 4 minus 2a squared minus 3 equals 0. Okay, is what we want to do. And so then we look at solving this. Okay, so there's a couple of different ways we can think about this. Okay, the textbook has just jumped straight into the answer, but I reckon we just go a little bit slower there and just go, well, let's say that m equals a squared. Well, then we have m squared minus 2m take 3 equals 0. Okay, that means that we're going to get m minus 3 and m plus 1 equals 0. And we'll sub our m equals a squared back in, so you get a squared minus 3 equals a squared plus 1 equals 0. And when we do the null factor law, okay, then this one's going to give us no solutions because we're going to get a squared equals -1. Okay, and we only want real solutions for this. Okay, so that we get a squared equals positive 3, so a equals plus or minus root 3. Okay, so then we substitute in for b, okay, and we knew that b was equal to root 3 on a. Okay, so that means that b is going to equal root 3 over plus or minus root 3. So b is going to equal plus or minus 1. Okay, b is going to equal plus or minus 1. So then when we're looking at z here, okay, really what we can say is that z now equals plus or minus z equals plus or minus root 3 plus I. Okay, because our a is plus or minus root 3 and our b is plus or minus 1, so we can just make our plus or minus out the front. Okay, that's how we look at it from a rectangular point of view. Okay, if we flip over, okay, so if we look at in polar form, okay, we'll always get two solutions. Okay, if z squared equals r cis of theta plus 2k pi, then z equals root r cis of theta on 2 plus k pi. And what we do is we let k equals 0 and k equals -1 into this solution to get the 2 that we need. Okay, and we note that the two roots are separated by 180 degrees. Okay, and the two roots are not complex conjugates, so it will look something like this. Our two answers are separated by 180 degrees. So what we do is we say for this one we've got z squared equals 2 plus 2 root 3 I. Okay, and note this is the same equations we used last time. Okay, so then basically we set up this equation here. Okay, so okay, what it is we get z squared, okay, is equal to 4 cis of pi on 3 plus 2k pi. Okay, that's from converting it to polar form. Okay, so you might need to look back with our polar form. Okay, so then that means that z is equal to, it's the square root of 4 cis of pi on 3 plus 2k pi on 2. Okay, so z is equal to 2 cis of pi on 6 plus k pi. Okay. So what we do then is we let k equal 0. Okay, then we get z equals 2 cis of pi on 6. So I say z is equal to 2 where cos of pi on 6, okay, plus I sine of pi on 6. Okay, we'll actually expand out so we get back to our rectangular form. Okay, so that is 2, well, our cos of pi on 6 is root 3 on 2, okay, plus I times a half. Okay, from sine of pi on 6, so cos of pi on 6 is our root 3 on 2, sine of pi on 6 is a half. Okay, multiply out by our 2 and we get our root 3 plus I. Okay, if we go back and do this same part with our -1, okay, then we get, let k equal -1, okay, then we get z equals 2 cis of minus 5 pi on 6, because we would be taking away pi. Okay, take pi away and we'll get -5 pi on 6. So then we get, that means that we've got 2 cos of -5 pi on 6, okay, plus I sine of -5 pi on 6. Okay, so from there we get 2 outside of cos of -5 pi on 6 is -root 3 on 2. Okay, plus I times -1/2. So we multiply that by 2, we get our negative root 3 take I. Okay, so then we can say all up that z equals our plus or minus root 3 plus I. Okay, so this is exactly the same answer as what we got previously. So it's just we've got to convert things into polar form, okay, and then utilise Gromard's theorem, okay, and then sub in values and convert them back to polar into our rectangular form. So there's a little bit of mucking around. Okay, we can also look at cube roots of complex plane. Again, they can be found in rectangular form or polar form. There'll be 3 solutions, okay, and they'll be 120 degrees apart from each other. Okay, so if we were to graph the ones that we just did, okay, we do actually end up with something like this. Okay, and this is our root 3 plus I, and this is our negative root 3 minus I. Okay, you can see that we're separated by 180 degrees. Okay, so this time with our cube roots, okay, we'll have 3 solutions. Okay, so it might be that we have one up here, one down here, and one down there. Okay, but it'll be separated by 120 degrees, that's the main thing. Okay, so we'll look at doing our rectangular form first. So we're saying that z cubed plus 8 equals 0. Okay, and we want to find it using our rectangular form. Okay, so what we want to do is use our sum of 2 cubes. Okay, so our a cubed plus b cubed equals our a plus b times by our a squared, take ab plus b squared. We want to use that formula. Okay, so what we look at is going, well, for here we've got z cubed plus 2 cubed is our equation. So we can say, well, we get, so our a is z and our b is 2. So we're going to say that we use z plus 2 outside of z squared minus 2z plus 4 equals 0. Okay. And keep going. So what we do is we complete the square on this part here. We get z plus 2. Okay, when we complete the square, we get z squared take 2z plus 1 take 3 equals 0. Okay, and we can fix that up a little bit more because we can say, well, that is z plus 2 is our z take 1 squared plus 3 equals 0. Okay, and what we can do is replace our I squared with negative 1. So what we, oh sorry, I missed a step, sorry. So z plus 2 z take 1 squared, okay, take 3i squared equals 0. Okay, so we're gonna run with that. Okay, so I'm just checking there. Yep. Okay, so what we want to do is then factorise the difference of 2 squares in here. So we're setting this up as difference of 2 squares inside our brackets. So when we come up here, we're going to be z plus 2, okay, and then we're going to be our z take 1 plus root 3i, and we're going to be z take 1 take root 3i, okay, equals 0. Okay, so remember when we finish off factorising in here, okay, it's going to be this, and we take square root of that, okay, or the same thing with plus square root of that. So that's how we end up with our 3 different terms there. Okay, so if we do our null factor law then, we get, well, our 3 roots being z equals negative 2. Okay, and then we get, for this one, okay, well, we're going to be z take 1 plus root 3i equals 0. So z is going to equal 1 minus root 3i. Okay, and for this one we go z minus 1 minus root 3i equals 0. Well, that's going to be z equals 1 plus root 3i. So all up we can say that we've got our three roots that are z equals minus 2 or z equals 1 plus or minus root 3i. Okay, so if we were to sketch those, okay, what we get there is that we've got one out here, we've got one there, we've got one out here, we've got one here. That's the way that one ends up working. Okay, again we can look at doing it in polar form. So really what we're doing is we're using R's theorem. So if z cubed equals r cis theta plus 2k pi, then our z is root 3r cis of theta plus 2k pi on 3. And to get our three solutions, we sub k equals 0, 1 and negative 1 into our equation here. Okay, and note, using other values for k, okay, the roots would just repeat themselves. So if we didn't use these values, if we chucked in say 2 or 5, something like that, we'd just be finding the same root over again anyway. Okay? So we've got z cubed plus 8i equals 0. Just going to separate that off. Okay, and we want to find the complex number z using the polar method. Okay, so we go z cubed equals negative 8i. Okay, and so we can say that's equal to 8 cis of negative pi on 2 plus 2k pi. Okay, so that's just turning into polar form. Okay, just turning into polar form. So we need to make sure that we remember how to do that. So just double check again if we need to. That means using Dewey's theorem that z equals the cubed root of 8 cis of negative pi on 6, okay, plus 2k pi on 3. Okay, and then what we do is we let k equal 0. So we go let our k equals 0. Okay, then z equals, well, cube root 8 is 2 cis of negative pi on 6. Okay, so that's our 2 cos of negative pi on 6 plus our sine, I sine of negative pi on 6. Okay, so we can keep going. Okay, we get 2 cos of negative pi on 6 is root 3 on 2. Okay, plus I times negative a half. Okay, the sine of negative pi on 6 is negative a half. Okay, multiply through by our 2, and we get root 3 minus I. That's one of our solutions. So that's one of our solutions there. Okay, we'll let k equal 1 this time. Okay, so this time we get z equals 2 cis. Okay, so if we put in here 1, then we've got negative pi on 6 plus 2 pi on 3. We think of that as 4 pi on 6. Okay, so we're going to be 3 pi on 6 or just pi on 2. Okay, when we put our 1 in there. Okay, so that means that we get 2 cos of pi on 2 plus I sine of pi on 2, which equals 2 outside of, well, cos of pi on 2 is 0, okay, plus 1 I sine of pi on 2 is just 1, okay, which means we get 2i, Okay, so that's our next one. Okay, I'll go over here for our last one. So that's when we go k equals -1. Okay, well we go z equals 2 cs of -5 pi on 6. Okay, that's going to be because when we put in -1 here, we're going to be -pi on 6. Take 2 pi on 3 or take 4 pi on 6. So -pi on 6, take 4 pi on 6 will give us our -5 pi on 6. So again, we say that, well, that's 2 cos of -5 pi on 6, okay, plus I sine of -5 pi on 6, okay, which gives us 2 outside of -√3 on 2 plus I times -1/2. Okay, so that means that we get -√3 take I. Okay, so all up, okay, our three answers are going to be z equals plus or minus √3 minus I. That takes into account this solution and this solution, okay, or 2I. Okay, that was our last solution. So we're almost there. Got one more worked example to do. That's when we talk about fourth roots. Okay, so again we use Meyer's theorem, as polar form is much easier. Rectangular form can still be used, but polar form is much easier for these ones. Okay, so again we use z equals the fourth root r cs of theta plus 2k pi on 4. This time we let k equal 0, -1, 1 or -2. And our answers will be 90 degrees apart. So see, each time they're going to be evenly spaced. Okay, so we'll start it off. We've got to solve z to the 4 plus 16 equals theta. Equals 0, not theta. Okay, so we say, well, our z to the 4 equals -16. Okay, for that one. Okay, which means that z to the 4 equals 16 cs of pi on 4 plus 2k pi on 4. I'm just going to leave it this time as 2 on 4, because last time in the previous example you see I kept on having to convert that anyway. Okay, so that means that z equals the fourth root of 16 cs. Oh, sorry, I jumped a step here. Sorry. And I'll go back and fix that in a second. Sorry, up at this stage, inside these brackets, we should have just been pi plus 2k pi. Okay, so this should have been what was in those brackets. Then when we use the Meyer's theorem, we get this. Okay, so from there we can start doing our work. So we can say let k equals 0 in this equation. Okay, then we're going to get z equals, well, the fourth root of 16 is 2. We get 2 cs. All this part drops out, so it'll just be pi on 4. Okay, so z equals 2 outside of cos of pi on 4 plus I sine of pi on 4. Okay, I'm hoping you're getting sick of me saying this stuff, because we're just following a pattern now. Okay, so that's 2 outside of root 2 on 2 plus I times root 2 on 2. Okay, which means we're root 2 plus root 2i. Okay, or in the textbook they write root 2 outside of 1 plus I. Either or, doesn't really matter. Okay, so that's our answer for k0. Okay, we let k equal 1 this time. Okay, well, z is going to equal 2 cs. Okay, well, we let 1 be here. Okay, then we're 2 pi on 4 plus pi on 4, so I'm going to be 3 pi on 4. Okay, so that means that we've got 2 outside of cos of 3 pi on 4 plus I sine of 3 pi on 4 Okay, cos of 3 pi on 4, okay, is negative root 2 on 2 plus I times root 2 on 2. Okay, so this time we get negative root 2, okay, and plus root 2I. Okay, or in the other way we can say root 2 outside of negative 1 plus I. Okay, so you can see we're a little bit different there. Okay, we'll let k equal negative 1 this time. Okay, then we're going to get z equals 2 cis of negative pi on 4. Okay, because in here when we make this negative 1, then we're pi on 4, take 2 pi on 4, which will give us negative pi on 4. Maybe 2 side of cos of negative pi on 4 plus I sine of negative pi on 4. Sorry, getting a little squish there. So it'll give us 2 outside of, well, our negative, cos of negative pi on 4 is root 2 on 2, okay, minus I times root 2 on 2. Okay, so it's just our sine of negative pi on 4 is negative, so we're just putting the negative with our I instead for there. So that just means that we end up with root 2 minus root 2I, okay, which we can write as root 2 outside of 1 minus I. Okay, so getting there. Last one, we're going to let k equal 2. There is get z equals 2 cis of minus 3 pi on 4. So if we put negative 2 in here, then we're going to be pi on 4, take 4 pi on 4, which is going to be minus 3 pi on 4. So then we can say, well, z is equal to 2 outside of cos of negative 3 pi on 4 plus I sine of negative 3 pi on 4. Okay, so z equals 2 outside of negative root 2 on 2. Okay, take I times root 2 on 2. So again, our sine of negative 3 pi on 4 is a negative root 2 on 2, so just putting that with our I. Okay, so that means that z is going to equal negative root 2 take root 2I. So z is going to equal negative root 2 outside of 1 plus I. Right like that. Okay, so now what we're going to do to finish off this tutorial is state all our answers. Okay, so you get z equals, we'll have 1 up there, root 2 outside of 1 plus I, and no one here, which is root 2 outside of negative 1 plus I. We had root 2 outside of 1 minus I, and we had negative root 2 outside of 1 plus I. Okay, so there we have it. So you can see there's very much a pattern to this. Okay, so I mean, despite the fact that in the early ones perhaps it seemed a little bit harder to do the polar form because there was converting back stuff. I think honestly, if you stick with the polar form stuff, you'll probably go a little bit better at this stuff because you can follow the same process over and over and over again. So hopefully that's enough to get you through these questions.